All right, welcome back to the deep dive. We've got some really interesting listener material to dig into today about, well, hold on to your hats, folks, Rayshon expressions, and how these things might be the key to figuring out like where the mass of those particles even comes from.
And then there's how they express themselves, so to speak, as these Rayshon expressions that are proposed to actually make up the quarks and leptons.
Okay, so these expressions, that's what we're focusing on today. The listener material mentions two main types, T and V. What are we talking about here?
Well, imagine the Rayshon as this fundamental entity, right? It's almost like a concept more than a thing. And it can express itself, manifest itself within space-time in these two ways, T and V.
Sort of like, I don't know, a letter can be uppercase or lowercase.
Yeah, that's a good analogy. You have the same fundamental letter, but it can take on different forms depending on the context. So a single Rayshon, same fundamental idea, can have a T-type expression or a V-type. And then these T and V expressions are what come together to build up those particles we know and love, like quarks and leptons.
Okay, so that's T and V, but it gets, well, kind of more complicated, right? Because the material also talks about generic, prime, and flavored kinds, all within groups of 3 Rayshons. It's a lot to keep track of. What's the deal with these distinctions?
Right, so the idea here is that Rayshons don't exist in isolation. They always come in these groups of 3, these fundamental triplets. And within that triplet, each Rayshon has to relate to the other two. These kinds, generic, prime, and flavored, are likely representing different aspects or relationships within that triplet.
So, like, I have 3 ingredients for a cake, but I can mix them slightly differently, maybe add a dash of this or that. I still have those 3 core ingredients, but the final product, the cake, can have subtle variations.
Precisely. You got it. And in our case, the cake would be a fundamental particle. So for both T and V expressions, within a group of 3 Rayshons, you have these 4 possibilities, the generic one and then 3 others, referred to as prime and flavored.
So hold on, let me do the math here. We've got T and V, that's 2, and then 4 kinds each.
So for a single Rayshon in a group of 3, considering both T and V types and those 4 kinds, you end up with 16 possible expressions.
16. Okay, yeah, I see. That's a lot of potential combinations, even at the super fundamental level. And if I'm getting this right, the key point here is that these Rayshon expressions, they're not little particles zipping around, right? They're more like the structure, the fabric of those quarks and leptons.
Exactly. It's a crucial distinction. They're not dynamic in that way, not little packets of energy. Instead, they're proposed to be the very stuff that makes up the space-time structure of those particles.
Makes sense. But then how does all this static stuff, this structure, lead to mass? Because particles, they have mass. That's kind of a big deal.
Right, and that's where things get even more interesting. The idea here is that the initial mass of a fundamental particle, it's not some random number assigned to it. It comes directly from the way those associated Rayshon fundamentals are arranged. The same ones, remember, that are also involved in forming the very structure of space-time.
So the mass is built into the fabric of the particle, literally woven into the space-time it's made of. That's a wild concept.
It is. And to understand it better, we need to talk about how those 6 Rayshon fundamentals, labeled A through F in the material, can be grouped together. The listener material highlights these 2 basis groups, ABC and DEF.
Okay, A, B, C, D, E, F, back to basics. Why are these groupings so important for understanding mass?
It's all about combinations. Think of it like this. The p-space-time structure of quarks and leptons, which are what we're trying to understand, they're built from combinations between these 2 basis groups.
Okay, so 2 different sets, A, B, C, and a D, F. We're mixing and matching.
Right, like having 2 sets of Lego bricks. You can't build as much with just one set, but when you combine pieces from both, the possibilities explode. In this case, the structures you can build are those fundamental particles.
Got it. More combinations, more possibilities. But how many ways can you actually arrange these things?
Well, the material says there are 20 different ways to configure those basis groups. That leads to 10 different ways of actually partitioning the 6 fundamental Rayshons. And each fundamental Rayshon can participate in 10 of these basis groups.
So a lot of potential arrangements going on. That must be important for the mass, right?
It is. This multitude of potential combinations, the material calls it the multiplexity of Rayshon expressions. It's central to how these initial masses are generated, because each specific arrangement, each permutation, leads to a different outcome.
Okay, that makes sense. But how do we get from those arrangements, those permutations, to an actual number, a mass value? That's what I'm still trying to wrap my head around.
All right, so this is where those P expressions come back into play. Remember how we said they're kind of special? The material proposes this rule. Each T expression, depending on how it's arranged with other T's within a generic quark or lepton, can multiply or divide those 20 permutations, the basis group configurations we talked about, by a factor of 1 or 10.
Okay, hold on, back up a sec. So the T expressions, they mess with those 20 permutations. How does that work?
Yeah, it's a bit intricate, but here's the gist. If you have two T expressions representing fundamentals within the same generic quark or lepton, they together contribute a factor of 1 to the mass calculation. If a T expression appears on its own, not paired with another T even, then it contributes a mass factor of 10.
All right, so two different T's together, factor of 1. Lone T, factor of 10. Got it. I'm starting to see how this might work. Let's try it out. What about the generic down quark, that basic one? How does this model explain its mass?
Okay, so the down quark, according to this framework, involves an anti-V doublet in its formation. And for the mass calculation, we look at the anti-T expressions. In the down quark, there's one singular anti-T.
Singular meaning it's on its own, so
Yeah.
factor of 10, right?
Right. And remember those 20 permutations from the basis groups. We multiply that factor of 10 by 20, and we get it.
200. 200, what are the units here?
Electron units, it's kind of a baseline unit of mass used in this model. So 200 electron units for the generic down quark.
200 for the down quark. Makes sense. But the up quark, right? That one's way heavier. How does that work out?
Okay, so the up quark, it's formed from the T of one doublet combining with a T of another. Two T expressions involved. But here's the key. Each of those T's represents a different Rishon fundamental.
Different. Okay, so they each get that factor of 10, right? Because they're so low.
You got it. So we've got a factor of 10 from one T and another factor of 10 from the other. Multiply those together, that's 100, and then multiply that by those 20 permutations.
Whoa, 2,000. That's a huge jump from the down quark's 200, just by having two different T's instead of one lonely anti-T.
That's right. That difference in those initial combinatorial arrangements, it has a huge impact on the mass. Now, what about the electron? It has a mass similar to the down quark, right? So how does that fit in?
Yeah, 200 electron units, I remember. But it's not a quark, it's a lepton.
True, but the same principles apply. The electron involves two anti-T expressions, but these represent the same fundamental Rishon within a basis group.
Same fundamental, so that means...
Factor of 1, because they're together representing the same fundamental Rishon. But there's also one singular anti-T present representing a different fundamental. That one gets a factor of 10. So we multiply. 1 times 10, that's 10 times those 20 permutations.
And we're back to 200 electron units. It's incredible, really. These seemingly simple rules about how those T expressions are arranged, they seem to predict the initial masses of these particles.
Exactly, and it's not just those three. The material suggests that the same framework can be applied to the middle generation particles too, like the strange quark and the muon.
So there's a pattern here, a deeper structure at play. That's mind-blowing.
What's really profound is this. The initial masses of those fundamental particles, they're not arbitrary. They emerge from the way those Rishon expressions, those fundamental building blocks of spacetime, are combined. It points towards this incredibly elegant underlying order in the universe.
Yeah, we started talking about the building blocks of the universe, and we ended up with, well, the blueprint, the instruction manual for how to put those blocks together and what shapes they make.
Precisely. And what's truly remarkable is that a single set of principles, this framework of Rishon expressions, might explain both the existence of these particles and their masses. It's a whole new way of looking at the fundamentals of reality.
It makes you think, doesn't it? Like, what if those constants we learned about, they're not really constant? What if they're just the outcome of this deeper, more fundamental set of rules, this combinatorial game played out at the smallest scales?
It's a fascinating thought, and it leads us to a final question for you, our listener, to ponder. If those initial masses, those seemingly fundamental properties of particles, are determined by these combinatorial configurations, what does that mean for our understanding of the forces that govern those particles? How does this affect our picture of the early universe, those first moments when everything was taking shape? Could the very structure of reality, from the smallest particles to the cosmos itself, be encoded in those fundamental arrangements?
That's something to think about. Thanks for joining us on The Deep Dive. We'll be back next time, exploring even more fascinating corners of the universe.